Buongiorno, Edo, and now it's your turn with your talk. A big round of applause for Edo.
Thank you. Thank you. Well, I'm happy to see so many people here, and it's quite late, second day after lunch. We are all tired, so I'm trying to get this talk a bit sparkling, okay? How many of you were here yesterday for Fermion's talk about WebAssembly? Okay. Okay. And honestly, how many of you pretty much know what WebAssembly is and how it works? Okay. I was hoping to skip one of the talk's part, but I cannot. Okay, I'm Edo, already David introduced me. If you want to contact me, I'm on Mastodon with this address, edo@continuousdeliver.social, @Dusi on any social. And I work on SparkFabric. SparkFabric is a consultancy firm based in Milan, but we are full remote. So if you want to join us, you can go to careers.sparkfabric.com. And we are looking for cloud-native engineers, Drupal developers, but if you are like a front-end developer, you can go with trying to contact us for open positions. And I have a couple of podcasts. You can follow me on YouTube and Spotify. I talk about tech news, okay? But today, I will skip this part. I want to talk about WebAssembly. Using WebAssembly. Actually, I don't use WebAssembly, but I was fascinated by WebAssembly. In 2018, maybe, I saw this tweet by Solomon Hykes, the creator of Docker. And this tweet goes, if Wasm and WasM is WebAssembly, WasI is a system interface, we'll see later. If WebAssembly existed in 2008, we wouldn't have needed to create Docker. And at the time, I was like, what? Like, Docker and WebAssembly, what Docker has to do with WebAssembly? I thought of WebAssembly like something to get Unity games running in browsers. That was my vision of WebAssembly at the time. And Solomon Hykes pointed out that Docker and WebAssembly basically can replace each other. And that's what brought me to study WebAssembly and see what WebAssembly really is and what I can do with WebAssembly. And I want to bring you with me in this journey. So let's start with a bit of a history. In the 70s, we have the formal definition of hypervisors, okay? So we found a way to virtualize systems, to add levels of abstractions on top of systems, okay? So we didn't have to write machine language or code that ran directly on machines, okay, but on abstractions, okay, on hypervisors. That was the 70s. Well, that was the 60s actually, but in the 70s we had the formal definition. And in 1999 we had VMware releasing Workstation 1.0, and we could add another level of abstractions. We could use virtual machines in our workflows. We could download the Workstation and run different operating systems in our operating systems. And that pretty much changed the way we worked at the time. And jump to 2013, and this is the first public presentation of Docker. Solomon Hykes here at the PyCon, and he changed the way we worked with containers, because working with containers was a pain in the ass at the time. But then, with Docker, we could easily work with containers in our local environment and in production. And the year after, AWS introduced Lambda. You see that we are moving on abstractions layers here. And I think this is actually the best way to explain WebAssembly, not as a virtual machine, or like sometimes I see that people try to compare WebAssembly to Java, because they both have a virtual machine, like a virtual machine like the JVM. In assembly, you have something like the JVM. But I think the best way to explain WebAssembly is actually talking about abstractions. Okay, and so here you see many levels of abstractions and the benefits that you have. And I think I can explain WebAssembly now that you get that moving in time, we tend to abstract our our hardware and focus on our business logic and focus on portability of software. Okay, being able to develop software for whatever architecture, port software to whatever architecture without having to focus on the underlying hardware. It's the benefit to being able to abstract. And with WebAssembly, we can do that. Because what is WebAssembly? It's actually a standard. It's a standard and a binary code, like a byte code. WebAssembly was created for the browsers. So I remember correctly, when I remembered the demo of a Unity game running in the browser, that was the first use for WebAssembly. They wanted something that could run desktop software in browsers using desktop capabilities, okay? And so they worked at Mozilla and then joined by Microsoft and Google and others to create a standard to get high-performant software in the browsers, because they wanted to have portable software, okay? And the browser was the perfect operating systems for that. And so they created this standard. But having something that you can port where you want is exactly what we are doing with containers, with serverless, and with functions in cloud. So that's familiar. So how WebAssembly works? I will go fast with it. We have three main things. You have a compiler. You can compile many languages to WebAssembly. Like you can compile Rust, you can compile Go, or others using tools that you have in the tool chain. Like for example, in the Rust tool chain, you have a WebAssembly compiler. But you can also use a standalone compiler like mscripted and compile languages. And you compile this language to WebAssembly. And then you have the binary format. When you compile, you obtain a byte code. And that's the binary format, the low-level representation of your code. And then you have the runtime. The runtime runs your byte code. Your runtime can be in browsers, of course. So you have softwares that runs in browsers. And then you have runtime that runs standalone. So for example, you have Wasm time. And also you have the runtime in Node. So you see that you can run this software, this runtime, pretty much wherever you want. You can run it in browsers, in Node, as standalone, like with Wasm time. And with this runtime, you can access system capabilities, such as files, the network, sockets, okay, or the graphics. So that's the three main parts, okay, of WebAssembly. Let's see. Let's keep this demo actually. That was a simple demo to show that you can have Rust code and import your Rust code in JavaScript, okay? Because compiling this allows you to export a function and import in JavaScript. But I want to show you a bit more complex example. Okay, here I have a function in Rust adding two numbers, two integers. So this is pretty simple, okay? Using WasmPack, you can compile WebAssembly and have a module that you can import in JavaScript. That's just to show you that's pretty easy to go from this code to our JavaScript application. This is my application, okay? I have this JavaScript application. I'm importing the JavaScript, the WebAssembly module, and I'm calling the add function. The add function, I wrote it in Rust. I'm adding a couple of numbers, and then I'm printing the result in my HTML. So you see, if I port this application in a browser, I have an application that's exposing a front end in JavaScript, but the business logic is written in Rust. So if I had something more complex than a sum, I would just execute this code, the one that outputs 92 in Rust. That's the result, okay? My business logic is written in Rust for getting this number, but the front end is exposed in JavaScript. So just to show you that you can go from a language and import it as a WASM module in JavaScript. We see what a WASM module is, and there's more. We have WASI. I told you about WASI in the beginning, and WASI is the thing that allows us to access system capabilities like you have the runtime, but you want to access the system capabilities, like you want to access the files, you want to access sockets, HTTP, and you can do that with WASI. It's basically an API, okay? The safety features that WASI adds are permissions that you must give to the runtime in order to access whatever capability. So for example, if you want your runtime to access files, you have to explicitly allow your runtime to access files. If you want to access HTTP, you have to explicitly allow your runtime to access HTTP. So this is the power. So if you run a WebAssembly application, it cannot use a capability without your explicit allowed. And in the preview 2, you see, the standard is pretty much not stable, okay? Nor WebAssembly nor WASI are stable standards. So you see, when you go and see the standards, you see lots of preview or 0 point something, because it's not something that's really stable. Although it's around for years, but it's not really stable. And the ecosystem around is pretty much a mess. But you see here, a couple of months ago, maybe 1 month ago, we saw the WASI preview 2, and in preview 2, we had like a split in 2 words. The WASI CLI that accesses files and sockets and clocks the systems, okay? And WASI HTTP that accesses the HTTP capabilities like responses and requests. So this is WASI. And for a demo of WASI, it's really simple. I wrote a simple Rust function to open a file, copy the content of this file, and write the content of a file to another. You see, it's pretty simple. I read the content of the file, I create a new file, and then I write all the content inside the new file. So you see, I need access to the file system in order to do that. I get args from the command line. So I compile using WASI as a target, using the toolchain of Rust. Okay. So I'm creating a new file, hello.txt. So if I'm calling this with the WASM time, assembly runtime, simply calling hello.txt and trying to copy it into /tmp, it gives me an error. So, and if I explicitly add the local directory capability, I get another error because I also have to allow to write into the /tmp directory. So doing that allows me to write into the /tmp directory. So if I cut the deny file, I can see the content of the hello.txt. So I have to explicitly allow my runtime to access those capabilities. So that's the easy demo. So main features here are performance, portability, and security. I think you guessed that. I don't want to focus on that. I want to focus on WebAssembly concepts. You have a stack machine with instructions. When you have your bytecode is composed of instructions like a stack machine. So every instruction is pushed on the stack, and when you run it, they are popped from the stack. So instructions and values are pushed and popped from a stack. You have also control instructions. And another important concept is that WebAssembly uses a linear memory. So every time you run a WebAssembly software, you get this linear memory allocated dynamically, so it can grow. But you have this linear memory. So every time you you allocate bytes, you get contiguous bytes allocated. Okay, so when you create an array, you have contiguous bytes, another array, another bytes. Okay, and if you try to access a memory area outside of the initial allocated memory, you get an error. So that's the memory safety capability of WebAssembly. Okay, you cannot access memory outside of your initially allocated memory. And then the third concept is modules. Every time you create a new binary in WebAssembly, you get what's called a module. And so the runtime basically runs your module. If you run multiple modules, you have isolated modules. So from a module, you cannot access the memory shared from another module. You don't have shared memory. So you have isolated memory. From a module, you cannot access the module, the memory that's used by another module. But you can export and import definitions. And that's crucial, because you can write an application, a software, with different modules that can communicate using exports and imports. So if you write a module with Rust and export a function from another module written in Go, for example, you can import that definition and use it. But in order to be able to do that, you have to have a way to translate functions and values from a language to another. Remember, at the beginning, we saw, for example, at the add function in Rust using two integers, okay? I wanted to add A and B, and I had 32 bits integers for A and 32 for B. And that's, WebAssembly supports only integers and floats, 32 and 64 bits. But not every language uses the same representation for data structures. Okay, so a string in Rust can be represented low level differently from a string in Go or for a string in C. So in order to be able to export a function definition from Rust and use it in C, you have to be able to translate this different value representation, okay? And that's where a new concept came recently, which is the component module. And the component module, you can think of components like a wrapper outside your module. So you have your module, your Rust program, your Rust function. You wrap your model, your Rust module with a component, and components are able to use interfaces to represent your values and functions in the same way that other modules use them. So if you have a function written in Rust, you export that function, the component modules takes care of representing your function with interfaces that other modules can use. And so you have interoperability. You can write a complex application using different source languages. Imagine you want to create an application and you have a team that's good in Rust, another team that's good with Go, and another with C. You can have your team write language, their preferred language, and you can compose their work using these component modules. It's still a work in progress, but it's pretty much the next way, okay, the future of WebAssembly. This is where they are going to allow interoperability, okay? I will use this intermission to drink. I will leave you with a plow. Thank you. Now, how many minutes have I? 10 minutes, okay. Now, you got what WebAssembly is, right? More or less. Now you should know more or less what WebAssembly is. Okay. So, but we still didn't answer the initial question. How can I use this with Docker or replacing Docker? So if you think of cloud computing, you think of distributed applications. So you can write a monolithic architecture application and bring it to the cloud. Okay, it's fine, but it's not what the cloud is useful for. You think of the cloud and you think of microservices. You think of distributed applications, a distributed architecture. And when you think of workloads in cloud, you want 4 main features. You want efficiency, flexibility, scalability, and security. And WebAssembly can answer to all these needs, because for efficiency, you have a compact binary that you can easily transfer between workloads. Okay, it's also optimized when it's compiled. And for flexibility, okay, you have plenty of languages that you can use as source. So flexibility is guaranteed. You can scale because each module is isolated from one another, so you can scale horizontally pretty easily. And security, you have sandboxing, so capability-based security. You have memory safety. You have isolation using the component model, and also using some of V8 features like isolates. Yesterday, the Fermion guy talked about Spin, which is an SDK for WebAssembly. I don't know. Yeah, think of Spin like serverless functions in WebAssembly, okay? So you write the functions, you upload this function to the Fermion cloud, and you have your cloud function written in Rust, for example, running in a cloud. But the same thing you can do with Cloudflare, with many others actually, like with Fastly, I think. But with Cloudflare, you basically have more or less the same thing. Cloudflare uses V8 underneath, and with V8, it gives you the possibility to deploy WASM modules. And let's see a demo of this. I don't know if you're familiar with the Cloudflare CLI, but it's pretty easy. You just use Wrangler, and with Wrangler you can generate a template, or well, a function from a template. So this is the experimental worker Rust template. Okay, so you run this template, you get a template generated in Rust. Okay, so you use whatever name you want for your worker, for your function. The source code is this. So you see, we are messing with the request and the response. Okay. So I'm just returning a response with a text. Okay. I could do whatever I want, of course, in this, because I can mess with the result, with the response. I compile using the CLI of Cloudflare, and then I can deploy this. And you see, I can simply deploy my Rust code. The Wrangler CLI takes care of compiling it, and the Cloudflare worker takes care of running it. So I'm writing Rust for the cloud, so I can get a cloud function written in Rust. I don't think there are many services that allow you to write cloud functions in Rust, so you can use Cloudflare or Fermion or Fastly thing, I think. So this is the cloud function, and you saw that you had my response. And talking about Docker, this is something that you can try right now in Docker. It's WasmEdge. Remember that we have many runtimes, okay, in WebAssembly. WasmEdge is one of them. It's a project developed by Second State, but Docker managed to integrate WasmEdge inside Docker. And if you use Docker Desktop from a certain version, you can use WasmEdge with Docker. And so from 4.15, if you use Docker Desktop, you can there's a checkbox. There's a checkbox. What? Okay, to enable WASM support. And what it's actually doing is enabling WasmEdge. So if I have the time, maybe 5 minutes, 10 minutes, okay. Basically, this is how the Docker engine works. So it's you can think of it as abstractions even there. If you want to manage your containers, okay, what you're doing is telling Docker to manage your containers, to spin up your containers, to get up, down, removed. Okay, so what you're doing is giving your Docker engine instructions. Docker engine takes your instructions and pass them to containerd. And containerd knows how to communicate with containers, but not directly with containers, but with abstraction layers. First with containerd shim, and then with runc. Runc is the process that actually manages the containers, okay, low level. And containerd shim is what allows, it's like an API, okay, what allows containerd to communicate with runc. So what happens if I substitute runc with another runtime, like WasmEdge, and underneath container with WASM module? Basically, I can give my Docker engine the same instructions, like spin up these modules, take down these modules, and the shim, WASM shim, passes my instructions to the WasmEdge runtime that manages WASM module. That's what's happening right now if you enable the WASM flag in Docker. And you can, write a Docker file containing a WASM module, which is pretty simple, okay, and build it using BuildX, because it's experimental with this platform, and you get this compiled into an OCI, okay. When you have this compiled, you can push it, okay, with the usual tags for Docker registry, okay. So this is a valid OCI, but with a module, with a WebAssembly module inside, and I can run it in Kubernetes, because Kubernetes uses containerd. So containerd can talk with my WebAssembly modules exactly as it talks with my container processes, okay? So I can substitute the shim and runc with the shim for Wasm time or for WasmEdge, okay? And so I can communicate with Kubernetes, saying to my pods to get containers or Wasm modules up and down, okay? It's the same thing. I can do that, what, 2 minutes? 3 minutes. I can write a pod, and using this runtime class, Wasm1, which I wrote here, telling him that it must use Wasm time as a handler, okay? This is a runtime class I wrote. I use this runtime class, and this is transparent. In my pod, I have a Wasm module instead of a container, but higher level, this is transparent. And also, in traffic, a couple of weeks ago, they managed to include WebAssembly in their proxy, and using WebAssembly allows developers to write plugins for traffic in other languages than Go, okay? Because WebAssembly supports more languages, and using HTTP-Wasm with the API of WASI, they can mess with HTTP, with responses and requests, with whatever language you want, supported by Wasm, okay? So this is the future, having an application written in different source languages, packed together, communicating using the component module with different module and interfaces, okay? This is where we're going. I don't know if I have time, but basically you can go into the W3C and see the WebAssembly working group. They're working on the language specification, okay? So I said previously that the WebAssembly ecosystem is a mess because there are multiple institutions, multiple groups that are ruling on WebAssembly, because the W3C is ruling on the language specification. So you can go to this working group and see what they're doing with the language spec. And then you can go to Bytecode Alliance and see what they're doing with things built around the WebAssembly core. For example, the runtime, so the Wasm time, for example, and other specification, WASI, for example, okay? So this is another foundation, the Bytecode Alliance. And then you have CNCF, because CNCF, because WebAssembly is a new thing for the cloud, they have to host projects that use WebAssembly, but they are aimed for the cloud. So in the WebAssembly landscape in CNCF, you see already many Wasm projects part of the CNCF landscape. Last thing, if you go and see this document, the State of WebAssembly 2023, you see many data and reports and surveys about what's the current state of the ecosystem, or the developers ecosystem around WebAssembly. And one interesting thing is this question, what is WebAssembly used for? And you see that already 14% of developers are using WebAssembly for serverless functions, which is pretty interesting because it's really a young feature, okay? But already 14%. Of course, the first thing is web applications. If you go and use Photoshop in cloud, that's WebAssembly. If you use Figma, that's WebAssembly. So for web application, it's an obvious choice. But already you see many other things using WebAssembly, and serverless is something that expected to grow in the future years. Okay, so that's what we are talking about, and see you on the next episode of Continuous Delivery, and thank you for your attention.
All right, everybody, questions? I have two questions. One is kind of assisted, and I would like to know what why was the cloud The plow then?
Okay, the plow.
That's the first question.
Because you see, this is an interesting story. It was the 18th century, okay? 18th century. 18th century is good, yeah. Yes, 18th century. 1800, in United States. 19th century, okay, 19th century. In United States, they were conquering the West, okay, they were conquering the West, so they're moving from the East to the West. But then, when they reached the Illinois, they started moving slowly, because they wanted to, arare, plow the ground, okay, but the ground was not soft like in the East. It was hard, it was full of roots. And so they had not a way to plow the ground, but one person, the legend wants that a person, the John Deere, you see many tractors with the John Deere logo, okay? They are green tractors, okay, with John Deere. John Deere saw a plow in a farm somewhere, and it was a steel plow. Other farmers were using iron plows, and using iron plows didn't allow them to plow the ground fast, because iron is something that you have to clean often, okay? And so they were very slow in moving west. But then John Deere saw the steel plow, and he used this steel to create his plows, okay, and started a market selling plows, and then using steel plows, they conquered the West in a few years, okay, and obviously disrupting the environment, but one single tool allowed a movement, a market, to change to change an ecosystem. So this was my, parallel with WebAssembly.
Okay, my second question is actually more serious.
Yeah.
And it's about the fact that, do you believe that the fact that this WASM is agnostic could finally solve the battle of languages? My language is better than yours. Mine is, the best, and Java is shit, PHP is shit, and Python is,
No, I was fighting with another guy for language supremacy. I think it's silly, and I don't think actually having a runtime is the solution. There's not because there's not a problem. If you like to write your application in a language, I cannot rule that you have to write it in another language, because I think mine is superior. But instead, having a runtime allows you to abstract, and so allows you to don't worry about instruction sets that are different. Like we have 3 or 4 instruction sets, but with WebAssembly we have only one. So writing whatever language you want, you have a single instruction set, you have a single runtime. You won't solve the languages fight, but you have a new, you have a new way, you have an easier way.
So maybe. Yeah,
but
I wish. Thank you.
Any other questions?
Apart the case where WebAssembly is used for converting language, that like the terrific example that you mentioned, things. Did you made any performance comparison running native versus on this kind of runtime? There is any significant difference or resource consumption?
For cloud,
yeah.
Well, for example, you have a significant performance gain if you think about the bootstrap, and like the cold start is you go from milliseconds that you have to start a cloud function, for example in AWS function, a Lambda, to microseconds starting a WASM module. So the performance of your logic is more or less the same. You have near native performance, but the cold start is way better. Okay, Fermion thinks that they are magnitudes than AWS, using the same logic, okay, for Bootstrap. So with modules, you can have functions that bootstrap really faster. But the performance of the business logic is more or less the same.
Any other questions? No? Perfect.
Thank you.
Yeah. Now, a big round of applause for Edo. And this is for you.
Thank you. Thank you.